So yesterday, we talked about the properties of waves. We talked about the two kinds of waves. So quick review, okay? The two types of waves are longitudinal and transverse. Okay, in a longitudinal wave, the oscillation and the direction of travel are parallel or longitudinal to each other. Okay, whereas in a transverse wave, the oscillation is 90 degrees to the direction of travel of the wave, perpendicular or transverse. Okay, remember that the length of one cycle is called. Oh, no, okay, the length of time for one cycle is a period. The actual physical length of one cycle is the wavelength, which we denote with this symbol here, lambda. Okay, always going to be measured in meters. Okay, we talked about amplitude. We reviewed all those other things, frequency, period, all that kind of stuff, and they still mean the same thing. Okay, they're just applied to waves. What we're looking at today is the relationship between the speed of a wave, the wavelength of a wave, and the frequency of a wave. Okay, now, when we talk about this, we are going to talk about some of the principles of how a wave travels. That's going to lead us into the stuff we cover after Christmas. Okay, but some things we have to understand. First and most important thing, in this formula, there is one property of the wave that cannot be changed after the wave has been produced. Okay? Once a wave is produced, one of these three things cannot change. That means that if one of the other two things changes, they both will have to change in order to keep the one thing that can't constant. Okay? So, the thing that can't change about a wave is its frequency. The frequency of a wave, once it is produced, cannot be changed. All right? If light is originally made and it is red in color, it is always going to be red in color. Other properties, okay, its wavelength can change, its speed can change. In fact, they have to change together, but the light will always look red. Okay? It's always going to have the same frequency. Okay? Same with sound. Once a sound is emitted, its pitch is always going to be the same. Okay? I can change new waves to have a different frequency, but that wave, once it's out, is always going to have that frequency. But it might change its speed, and then its wavelength would have to change. But the frequency will always remain the same. You're going to hear me say frequency never changes. Frequency remains the same 100 times in this unit, at least. Is it something important to know? Okay, it's super important to know. Now, the universal wave equation is something that we can see, okay, kind of easily in nature, okay, or in even just the regular physical world. So, let's say we're going to use traffic to represent a series of waves. Okay? We're going to say that the distance between the cars is going to represent the wavelength of the waves. The speed of the cars is going to be the speed of the waves. And how many cars go by every second is going to be the frequency of the waves. So let's imagine that we're out here, we're just coming into Okotoks on Highway 2A, okay, and the speed limit changes from 100 to 80. All right? Now, many of you probably have your license, right? How close are you supposed to follow to somebody? Yeah, a 2-second following distance. Okay? Is it always 2 seconds, regardless of how fast you're going? Is the distance that 2 seconds represents always the same? No, it's not. That 2 seconds is like the period or the frequency of the wave. Okay? Depending on how fast you're going, that 2 seconds could represent a different wavelength because you're going a different speed. Now, what happens to it? If you're going faster, what happens to the wavelength or distance that 2 seconds represents? It increases. The same is true for the universal wave equation. So let's say that right here is where the speed limit changes from 100 to 80. Okay? So out here, cars are going 100. Here they're going 80. Okay? So out here, we've got 3 cars. And they're roughly the same distance apart. Okay? So the distance they are apart represents their wavelength. They're all traveling at 100 kilometers per hour. Now, which one's going to enter the 80 first? The first one, right? Okay, it's going to slow down. What about the other ones? But they're going to maintain speed until they get to the 80 line. Okay, so what will happen to the distance between them? It'll shrink. Okay, out here, if I'm standing here as an observer, I'm going to see 3 cars go by every second. Okay, when all 3 cars are in here, they're going to be traveling slower, but when this one slows down, the other 2 will catch up to it. Okay, and then when this one slows down, the back one will catch up to it. So on this side where they're going 80, those 3 cars are going to look like that. They're going slower. The distance between them has decreased, but as an observer, I still see 3 cars go by every second. The frequency of the cars going by, which is an analogy for waves, never changes. Because if the wavelength changes, the speed has to change, and vice versa. Okay? If a wave slows down, naturally the front of the wave will slow down first, and the back of the wave will catch up, making the wave shorter. Anytime a wave slows down, it also gets shorter. Anytime a wave speeds up, okay, the front of the wave runs away from the back of the wave. Okay, and the wave gets longer. So anytime a wave speeds up, the wave also gets longer. That's how the frequency is always maintained. Okay? Frequency is just that one property of a wave that can never change. Counting, I think that's 5 times that I've said that already today. Okay? So that property cannot change because the other 2 are always changing together. Okay? The only way to change frequency is to make new waves with a different frequency. Those waves can never have their frequency changed. Okay? You cannot change the frequency of a wave once it is produced. Okay? Probably want to give him a hand. He's got his hands full. Okay, so the universal wave equation looks like this. V equals lambda times F. It can also be written like this. V equals lambda over T. Okay, they mean the same thing because F is 1 over T. Okay? But you typically only see it written like this. You just have to know that that would also be true. If I manipulate this equation to solve for F, it becomes V over lambda, or speed over wavelength. Okay? So this is what we were just talking about. If the speed changes and the frequency can't change, then the wavelength has to change too. And it has to change in exactly the same way. If I double the speed, the wavelength has to double, because the ratio between them has to stay the same, because the ratio between them is the frequency of the waves. Okay, everybody all right with that? All right. Is this a very mathematically challenging formula? Okay, then any questions to do with it have to have tricks in them, right? Okay, so we're going to look at a few situations where this applies and look at the different kinds of tricks. Sometimes they have to do with the formation of waves or the structure of waves. Sometimes they're just a word trick, okay, but we have to understand them so we know what to do when we encounter them. Okay, so how fast does a traveling wave move? Well, if I wanted to find the speed of something, I could just use V equals d over t. But sometimes it's kind of hard to measure how far a wave has traveled because, especially like a water wave, its shape is always kind of changing and it's hard to tell where it starts and where it ends. Okay, so unless I can mark a certain spot on the wave and time it in a fixed distance, it's pretty hard to use V equals d over t for a wave. Okay, but I can use the properties of the waves, which might be easier to come by, to get that speed. But when I do this, when I go lambda over period, am I taking the distance a wave travels in one cycle and dividing it by the time for one cycle? That's still going to give me meters per second? It's really just d over t, but for waves. Okay, this is still the same. Remember that lambda times frequency, okay, is still going to be meters, but now it's multiplied by cycles per second. I'm still going to get meters per second. Okay, the cycles kind of goes away. Hertz actually means per second. Okay, everyone all right with that idea? Okay. So this is what we were talking about a little bit yesterday. Okay, out in the deep ocean, okay, a wave could have a very long wavelength. But as it approaches the shore and starts to interact with the bottom a little bit more, it slows down. Naturally, the front of the wave encounters the shallower water first. So it slows down, the back of the wave catches up, and you end up with shorter waves that get taller. Okay? And they tend to break as well. That is that rotational bit that we talked about, tends to make them curl a little bit. Okay? Are they still going to have the same frequency as the waves did in the deep water? Yeah. Yes, they are. Okay. Don't know what that one was for. All right, so this is the wave equation. Okay, this is what we were just talking about. V equals lambda over t, or V equals F times lambda, same thing. Okay, we can just use those properties of waves that are maybe easier to measure. Like I could get the period of a wave pretty easily if I was sitting in a boat and the wave went by. Right? All I'd have to do is time when I'm on the top of a crest, start the timer, and when I'm on top of the next crest, is one period gone by? One cycle? Then I'd have the period of the wave. Okay? And if I knew how far away that other wave was, I'd have the wavelength of the wave. They're just easier things to get than D and T for a wave. Okay. Oh, now I remember what that blank slide was for. Okay. Okay. What if a question says to me, 6 crests have a length of 10 meters. What's the wavelength? How would I calculate that? Did I draw 6? I did. Okay, 6 crests are 10 meters. So the distance from here to here is 10 meters. It'd be 2 meters. How many people are like, wait a minute, 10 divided by 6 is not 2? It's okay to think that. Most people do. How many wave cycles are there in the diagram I just drew? First crest to last crest? 5. Okay, we're starting here. That's 1 cycle, 2 cycles, 3 cycles, 4 cycles, 5 cycles. 6 crests isn't 6 cycles. The first crest is 0. That's where we start. Okay? The same is true for troughs, obviously. Okay? So that's one of the little context tricks that can come up in a universal wave equation question. They tell you how many crests or troughs go by. You got to remember that the number of cycles that went by is always 1 less than the number of crests or troughs. Okay? It's a very, very common wave equation trick. Okay? All right. Here's another thing that can come up with these kinds of questions. Let's say I've got a ship. I don't draw well. You guys know that. That's it. Okay? It's a sailboat. All right, but it's got sonar on board. Okay? And it sends down some waves to the bottom. Okay? And I find that I hear the echo from these waves back 4 seconds later. Okay? Speed of sound in water is 1,560 meters per second. Okay? How deep is the water?
Meters.
How much?
390 meters.
390 meters. That seems about big. Did you divide by 4?
Yes.
Okay. 4 seconds is how long it takes the sound to get to the bottom and back. What did I want? just to the bottom. Echo questions are always like that. Echo questions will tell you how long it takes the echo to come back. How far is an echo travel? There and back again. Echo questions are always going to be like that. You just have to understand that an echo is the reflection of a wave. And when you hear it, it has traveled twice the distance you're probably looking for. Okay, so that's another type of contextual trick that can come up for universal wave equation questions. Echoes always have the wave travel twice the distance. So either half the time or calculate the distance and divide it by 2. Okay, all right. So easy kind of universal wave equation question here. I got a sound wave that's got a frequency of 262 hertz. Okay, it has a wavelength of 1.29 meters. What's the, well, it says velocity, should be speed of the sound wave. All right, well, V equals lambda times F, 1.29 times 262 equals 338 meters per second. All right, pretty simple formula to use. Once you get the numbers for it, it's super easy to use. It's V equals D over T. Okay, it's not going to mathematically challenge you at all. It's getting the numbers in it right. All right, a couple of other things that can come up. What if a question says you're dealing with electromagnetic waves? All electromagnetic waves are a form of what? Energy? Yeah, what kind in particular? Starts with L. Light. Light. Any electromagnetic wave then travels at what speed? The speed of light. Another little thing, right? They're not going to outright tell you, hey, you got these radio waves that are, plugging along, and it's not going to tell you that they're traveling at 3.00 times 10 to the 8 meters per second. You have to know that radio waves are electromagnetic waves, which are light, which travel at the speed of light. Okay? Just again, little contextual tricks. Okay? One last little thing that can come up is this formula. It is on your formula sheet. V equals, is it 330 or 332? Changed it a little while ago. 332. Okay. 332, okay, plus 0.6 times T. That T is not period. That T is temperature. So occasionally, you will get a question about sound waves. And it'll tell you the temperature of the air that these waves are traveling through. The temperature of the air affects the properties of the air. The air is the medium. If you change the properties of the medium, you change the speed at which the waves travel through it. Speed of sound increases with warmer air. Okay, so all you do is go at 0 degrees Celsius, sound travels at 332 meters per second. For every degree Celsius you go up, the speed increases by 0.6 meters per second. So 332 plus 0.6 times the temperature in degrees Celsius. Okay, that includes when you go into the negatives. Make it negative and it works out just fine because then you're adding a negative number. Okay, will give you the speed of sound in the air of that temperature. And that formula comes up quite a bit today. Okay. All right, questions on that? Like I said, today you are not going to be challenged mathematically, okay, in any way, shape, or form. You're going to be using like these two formulas and V equals D over T a little bit. Okay, so nothing going to be super difficult that way. All right, I want you to write this one down and give it a try. Okay, I'll give you a few minutes on it. All right, so the person's sitting on a dock and they notice that in 30 seconds, 6 crests go by. How many waves went by? 5. Okay, so in 30 seconds, 5 went by, so I can either get the period or the frequency here. I'm just going to go and get the period. 30 divided by 5 will give me seconds per wave. Okay, so that is going to be 6 seconds as the period of the wave. Okay, the distance between the crests is 4.5 meters. What did they give me there? Not distance, wavelength. Okay, remember the distance between any two successive points on a wave, crest to crest, is the wavelength. So they told me what lambda is, 4.5 meters. What's the speed of the wave? V equals lambda over T. I can use that without having to do the 1 over F. If you do the 1 over F, that's fine. Okay, so 4.5 divided by 6, okay, will get us the speed of the waves there. I forgot to start my calculator. What does that come out to? 0.75? 0.75 meters per second is the speed of those waves. Everyone all right with that? Okay. So like I said, these are not going to be super challenging. All right, try this one. Write this one down and give it a try. This is an echo question. So we have a hiker who yells at a cliff, because who likes cliffs? They're always in the way and they're hard to climb. Okay, so they yell at it and they hear the echo 3.5 seconds later. On this day, the temperature is 22 degrees Celsius. How far away is the cliff? All right, so we're looking for D. All right, we're going to need V, and they gave me the temperature. So how do I get it?
V equals 332 plus 0.6 times T, or temperature.
Right, times the temperature, times 22. All right, so that's going to get me the speed on this particular day. So 332 plus 0.6 times 22 degrees is going to give me 345.2 meters per second. Now that I've got that, okay, now I need to find the time. Or sorry, I'm going to need to find, how far away the cliff is. Is this the time I want to use? If I use that time, what do I have to do with the distance I calculate with it? Divided by 2, because that's the distance to the cliff and back, and echo travels there and back. So I can do it that way, or I can just divide 3.5 by 2 right off the bat and say that the time is 1.75 seconds instead. Either way will get you the right answer, as long as you remember to divide something by 2 before you have your final answer. All right, so D is going to equal V times T, 345.2 times 1.75 seconds. A times 1.75. So that cliff is 604 meters away. Actually, we only have, what, 2 significant digits there, so 6.0 times 10 to the 2 meters. Okay, pretty straightforward. Alrighty, I would like you guys to try 2 and 3. Number 1 is too simplistic, so we'll try 2 and 3 there. Okay, answers are on the board. You can check your. Okay, so with number 3, probably a lot of you converted the meters to seconds, but you didn't have to actually. In the end, we were looking for meters, so you could leave the time in minutes through the whole thing if you wanted to, and it wouldn't make any difference. Okay, so here's what we know. We know the distance to the shore is 250 meters. We know the time to the shore is 3 minutes. And we know the frequency is 8 waves per minute. Okay, they tell us all that. The dinghy rises and falls 8 times per minute. It takes 3 minutes for a wave to reach the shore. What are we looking for? Wavelength, the distance between the crests, right? That's wavelength. So that's one of those context things. You have to know that the distance between 2 crests is a wavelength. All right, so if I'm going to get wavelength, then I need V and F. Okay, I don't have those things yet. It's not going to be times F, sorry. Okay, but I'm going to need V and F. I have F, but I don't have V. But I can get V because I have both distance and time. Okay, so I can take the 250 meters and divide it by 3 minutes. Okay, so 250 divided by 3 minutes. Okay, is giving me 83.333 meters per minute. Meters per minute. Which is, I mean, that's unusual. We don't use that very often, but they gave me the frequency in waves per minute. My units match, so I don't have to go out of my way to change them if I don't want to. All right, now that I know V, now I can say, okay, V equals F times lambda, and just manipulate to get lambda by itself. So I take my 83.3 and I divide it by 8 waves per minute, and I'm going to get to 2 significant digits, 10 meters. Okay, that's the wavelength of the waves. Okay, everybody all right with that one? A few context tricks in that one, and that unit thing that made probably a lot of work for you that you now realize you didn't have to do, but doesn't end up making you do it wrong. It just makes more work. All right. Okay, I would like you guys to try 5 and 6 there. Okay? They're not super hard, but I want to do something with each one of those questions. 5, because number 5 probably didn't take you very long. Okay, sound waves travel through seawater at 1,500 meters per second. What would their frequency be if they had a wavelength of 1.25 meters? All right, well, V equals F times lambda, so F equals V over lambda, okay? And that's going to be 1,500 divided by 1.25. Okay, so 1,500 divided by 1.25 is going to give me 1,200 hertz for their frequency. Now, if that wave is coming up towards the surface of the water and I'm on a boat, will I hear a frequency of 1,200 hertz when it leaves the water and enters the air? What property of a wave never changes? That's important for number 6. All right, so number 6 is not mathematically challenging, but you don't get it right if you can't apply the idea that frequency of a wave never changes. Okay, so that means the frequency I would detect with a wavelength of 2 and a speed of 1,500 is the same frequency I would detect if suddenly the speed of the wave changed to 1,550. Okay, that will allow me to calculate the new wavelength. There's 2 ways to do that. Okay, if I know that frequency is V over lambda, and I know that the frequency can't change, I could say that the ratio between these things here is the same. Agreed? All right, so all I would have to do is solve for lambda final. That would be what it is when it's 1,550, okay, by kind of manipulating this around. So I would just go lambda 1 over V1, okay, is equal to lambda F over Vf, right, and then just multiply both sides by Vf to get lambda F by itself. Okay, so I take my 1,550, multiply that by 2 meters, okay, and then divide that by 1,500, okay, and I should get that yes, okay, the wavelength is slightly longer when the speed is slightly faster. They have to change in the same way. All right? Everybody okay with that idea? That's the kind of thing that could easily end up as a written response question on a unit exam. It isn't a mathematically hard question, but it checks. Do you understand this concept? Not did you memorize frequency can't change, but can you apply it? Can you recognize when that's important? Okay. All right, I'm going to give you guys about a 5-minute break here, and then we're going to move on to some other wave equation kind of problems here. Okay, another question that kind of builds on what we were just talking about. Okay, I'd like you to try this one. Okay, 2 tuning forks are generating waves with a frequency of 384 hertz. The waves from one tuning fork are generated in air, where the speed of sound is 350 meters per second. The other tuning fork is generating sound underwater, which, take it from me, that's a neat trick. Okay, if you put a tuning fork that's vibrating in water, it splashes. Okay, it doesn't work nearly as well. Okay, as one that's in air. They're not really designed to work in the water. But we'll say that it is, where the speed of sound is 1,500 meters per second. Calculate the wavelength for the sound in air, the wavelength for the sound in water. Okay, and then we'll talk about C, which requires no calculation. Okay, let's quickly look at this one here, guys. It's not terribly difficult. We want to calculate the wavelength of the sound in air and the wavelength of sound in water. Well, wavelength is just V over F, 384. Hertz is, sorry, that goes on the bottom. The speed in air is 350 divided by 384. Okay, so speed in air divided by frequency. So 350 divided by 384 gives me a wavelength of 0.911 meters. in air. Okay, in the water, the speed is 1,500 meters per second. Is the frequency still 384?
Yeah.
It is. I'm using a tuning fork with a frequency of 384 hertz. Okay. All right, is the wavelength going to be longer or shorter? Longer, yeah, definitely. Okay, if it's a faster speed, then it has to be a longer wavelength. Okay, so 3.91 now for the wavelength in the water. Do you hear the same sound? Same frequency?
Yeah.
Yes. The sound might sound different, but that's not that the pitch is different. You would still hear the same pitch, but our ears don't work as well underwater as they do in air. Our eardrums are not designed or evolved to work in water. We don't spend much time underwater. Okay, so they're evolved to help us hear in the air. Right? But we would still hear the same pitch. This goes back to the synchronized swimming example I used earlier. Okay, but if you've got a team of synchronized swimmers, when the ones that are under the water and the ones that are above the water, they hear the same song. Okay, they're hearing the same pitch, the same music. Okay, the only concern would be if the pool was big enough, they might get out of time. They might not stay synchronized because the swimmers above the water, the sound would take longer to get to them than it would if they were underwater. Remember, sound in air only travels at 340 meters per second. Underwater, it travels at 1,500 meters per second. If you make the distance between the speakers and the swimmers too great, the swimmers under the water are hearing the song before the people above, and then they might get out of sync. Okay? It doesn't really affect it too much given the small distances they would use. Okay? But if the pool was big enough or they were doing it in the ocean, it might be a problem. All right, I would like you guys working on this worksheet. It's in the digital workbook, okay, and it's in the workbook, okay, and it is on page 3. Starts on page 3. Okay, it's wave transmission and the universal wave equation. Shouldn't take us long to get through that. Okay, so there's 7 questions on page 3, and then there's some more on page 4. Okay, so I'll leave these ones up for now, and then I'll scroll up in a little bit. Of course, if you've got it printed, then you're set already. Okay, remember that on some of these, that stuff I was telling you about earlier applies. If it's electromagnetic radiation of any kind, it travels at what speed? Light speed, okay, which is on your formula sheet on the back. Okay, so any kind of EMR, that's the speed. Sound waves, you might be given the temperature, you gotta use the 332 formula. Okay, that kind of stuff can come up here.